So the last thing I mentioned was the concept of a dominant strategy. And together with the concept of a dominant strategy, we can mention the concept of a dominated strategy. A dominated strategy is a strategy that is dominated by all the other strategy present in the game. So here we have an example of a game with 3 different strategies. So we have strategy F1, F2, and F3, and we have strategies C1, C2, and C3. So the strategies for the player in the file are different from the strategies for the player in the columns. So in this case, we have the payoff of the file against the column, and here of the column against the file. Okay? So let's see if we can use the concept of a dominated strategy to decide which would be the strategy chosen here by the 2 players. Maybe we can do it, or maybe we cannot. Obviously, this example was just built up in order to be able to eliminate, or following a process of elimination of dominated strategies to finally get only one choice. So if you look at the strategies, you can see that, for example, here, in this case, the player in the column will never choose the strategy C1. Why? Because 40 and 30 are bigger than 20. The C1, okay, yes. So 30 is bigger than 20, 50 is bigger than 21, and 25 is bigger than 22, okay? So the strategy C1 is dominated by strategy C3, so the strategy C1 will never be chosen by any player. Now, what we have is that the strategy F2 will never be chosen by the player in the file. Why? Because remember that this was not here because the strategy C1 was eliminated. So if we look at this situation, we can see that 60 is greater than 35 and 55 is greater than 30. So the strategy F2 is dominated by strategy F3. In this case, it is also dominated by strategy F1, okay? So we have eliminated the strategy C1 and we have eliminated the strategy F2. Next, we can eliminate strategy C3 because 40 is greater than 30 and 30 here is greater than 25. 10 is not greater than 50, but this situation was already eliminated because F2 was a dominated strategy. So we can now eliminate the possibility of choosing strategy C3. So we know that the player at the column will choose strategy C2. And if the player at the column will choose strategy C2, so finally the player at the file will choose strategy F3 because F3 has a higher payoff than strategy F1. So finally, this is what we have. So by eliminating this dominated strategy, we finally know what will be the choice in this game. So the player at the file will choose strategy F3, and the player at the column will choose strategy C2. Okay. So this is one of the situations where we can just decide and eliminate strategies. It is not true that this procedure can be always done by any game. Sometimes we can do that, and sometimes we cannot. Okay. There is a concept that is very important, and this is the concept of best response. Suppose that we have n players, okay? And each player, I, adopts one strategy among a set of possible strategies that we will call Si. A given strategy Si, or lower Si, that belongs to the set of possible strategies is a best strategy response, or a best response to the strategy of the opponent is O if no other strategy in the set of possible strategies gets a higher payoff. That means the following, that the payoff of the strategy SI against SO is the highest strategy, the highest possible strategy. Any other strategy, here we have, or maybe I will write it here to make it more clear. So suppose that I have strategy is SI, and I say that SI is the best response to SO. So the payoff of SI against SO is greater or equal of the payoff of SJ against SO for any J different from O, J different from I. Okay. Well, this is not true. This, okay? This is the best response. So given a strategy, there is another strategy that will get the highest payoff when I play this one. So I am playing SO, so I'm saying that SI is the best response to SO if the payoff of SI is the highest payoff, the highest possible payoff. So this is what we call the best response to a given strategy. Another important concept in game theory is the concept of Nash equilibrium. We said that a Nash equilibrium is a strategy that is a best response to itself. That's why when I put here, this is not right, okay? We need this because to define the concept of Nash equilibrium, we need a strategy that is the best response to itself, okay? Or in a case that we have different strategies, for example, as in the example before, that we have a different strategy for the file, a strategy for the file, or a set of strategies for the file, and a different set of strategies for the column. In this case, what we said is that a Nash equilibrium is a strategy that is the best response to itself, or a set of strategies that are mutually best responses one to the other, okay? No, no.
No era que en el anterior lo que llegamos no era un equilibrio Nash necesariamente.
Well, in this case, yes, it is. Why not?
Porque si el player F piensa que si el player F piensa que el player C va a elegir C2 y el player C2 piensa que F va a elegir F3, entonces la mejor respuesta del F es elegir F1. Porque sobrevivió el F3C2.
Yeah, but I mean, what you are doing by eliminating this is just obtaining the Nash equilibrium. Because suppose that, so from the beginning, I know that, for example, the player C1 will not choose this strategy, okay? So given that this player will not choose this strategy, now I can say that this player will not choose this strategy. Okay. Before knowing that, I was not able to say that. I was not able to eliminate the strategy F2. But once I know that C will not choose C1, then I can say that EF will not choose F2. Okay. And now I can say that the player C will never choose the strategy C3. So now I can say that the player F will never choose the strategy F1. So there is only one possibility.
Maybe I am mixed. The first value is for F, the second value for C.
Yes.
I have.
Okay.
Thank you.
So in this case, this is the Nash equilibrium, because if the player F changes the strategy, the player C will get a higher or has the possibility of having a better payoff. So now the player F can change the strategy, and finally they will end up by choosing this situation here. This is the only situation that is a sort of equilibrium. Okay?
Okay, thank you.
Marcelo, this question is bugging me. Why the payoff from one player is different than the payoff for the other player?
Because the game...
It's an unequal game, sounds like.
No, well, if you have a symmetric game, so this cannot happen. But there are some asymmetric games. This one is an asymmetric game. Okay, so it is not that you always need to have a symmetric game. You may have different matrices for different players. So this is called an asymmetric game, and instead of one payoff matrix, you need two payoff matrices. And also, for example, you may have a situation when you have two strategies for, I may have, for example, F1 and F2, and C1, C2, and C3. So the number of strategies doesn't need to be the same. So in this case, I will need two matrices. One matrix of this shape, one of this shape, where I have for F1 and F2 the payoff of each of these strategies against each of these strategies. And also I will need another matrix of the form where I have C1, C2, and C3, and here F1 and F2. This is called a B-matrix game, when the game is not symmetric, okay? This is an example of a non-symmetric game, and you can have something like that. Okay. Yes.
Hola. With my bi-matrix game, it means, I want to know, it the same that say that players are not equal. It's different, the position of player 1 and 2.
Yes.
You cannot interchange, right?
Yes, yes,
Okay.
yes. Yeah, the most common situation, or generally the examples for the games are symmetric games, when the two players are alike. But you may have a situation where each player, or we have two groups of players, for example, file players and column players, and the payoffs are different. And maybe the players that have the name file can only choose between two strategies, and the players that have the name column can choose between three strategies. So this is something that is okay and is within the frame of game theory. As I mentioned, if you have only one matrices and the players are the same, you are talking about symmetric games. And if they are not the same, you are talking about asymmetric games. So this is Nash, a picture of Nash. So a Nash equilibrium is reached when, and this is maybe a way of putting into words what we have defined in the former slide. A Nash equilibrium is reached when each player chooses a strategy that is the best option, given what the opponents are doing. So it is not convenient for any of the players to deviate from the chosen strategy. So in this example, it was not convenient either for F3 or for F or C to deviate from this choice. So the best thing for F and for C was to choose F3 as strategy and C2 as strategy. Okay? So this is a Nash equilibrium. So a Nash equilibrium involves strategic choices that, once made, provide no incentive for players to alter their behavior. So once we have reached the Nash equilibrium, there is nothing, there are no incentives to move from the Nash equilibrium, because there there is no way to be in a better situation. So if it is the best choice for each player given the other player's equilibrium strategy. So this is the definition of the Nash equilibrium. Any game in which the players have a finite numbers of possible strategies has an equilibrium in terms of mixed strategies. So sometimes this is something.
Marcelo,
Yes.
is there any difference in the Nash equilibrium perspective when you are in a zero-sum game?
Yes. No, the definition is the same one.
Okay.
No, sometimes what happens, I will show you an example of a zero-sum game where you cannot find a Nash equilibrium in terms of the strategies, the pure strategies, but you can get a Nash equilibrium in terms of mixed strategies. But this is a concept that I will mention maybe tomorrow. Okay, so that's why this is something that should not be here because I have not talked yet about mixed strategies. So this will appear maybe tomorrow again. This is not the right place to put it. Okay. So sometimes you can find, and this is something that I will mention now, sometimes it is not possible to find a Nash equilibrium in a trivial way. Suppose that this is the game of stone, paper, and scissors. This is a zero-sum game. This is an example that maybe will give you an answer. So this is stone, this is paper, and this is scissors. And again, we have here stone, paper, and scissors. So stones against stone is 0-0. You cannot see that, but this is 0-0. Paper against paper is 0-0. And scissor against scissor is 0-0. But paper against stone, it is paper that will win 1 and stone will lose 1. Paper against scissor will lose 1 and the scissor will get 1, and the same for the rest of the table. So this is the payoff matrix for the game scissors, stone, and paper. Suppose that we start here. So we both play stone in the first game, in the first round. So we start here. So the player at the column decides that will change the strategy and will start to play, for example, or the player here in the column will change and will play paper, okay? Because if the column is playing stone, for the player at the file, the best thing to do is to play paper. So this individual will change the strategy and will start to play paper, while the individual in the column will go on playing stone. But once this individual in the column realizes that the other player is playing paper, will change the strategy and will start to play scissor. Okay, if this one is playing paper, the player at the column will start to play scissor. So once this start to play scissor, the payoff for the column is higher than the payoff for the file. So once the player at the file realizes that the player at the column is playing scissor, will change the strategy and what will choose. So what we'll choose was to play stone, because if the player at the column is playing scissor, the player at the file will choose to play stone, because now stone is stronger than scissor and the payoffs will be reversed. So now it is the player at the file that is winning 1 and the player at the column that is losing 1. So once this change was made, the player at the column will decide to change again and will go here, and then the other player will decide to change and will go here, and then we'll go here and here, and we are the same. We are again in the same starting point. So from here I go to here, and so we have said that the Nash equilibrium is a situation where there is no incentive to change strategy. But here we see that there is always an incentive to change strategy. So the conclusion is that apparently there is no Nash equilibrium here. And it is true that there is no Nash equilibrium in terms of only considering these strategies, these pure strategies. Okay? But we will see that we can make a combination of strategies. Instead of playing always stone, always paper, or always scissor, maybe we can play, I will somehow spoil the answer, but if we play 1/3 of each of the strategies, so we will reach a Nash equilibrium. So the Nash equilibrium is not written in terms of only pure strategy. It's not written in terms of only stone, paper, or scissor, but it is written in terms of a combination of the three strategies that are present here. Okay. Sometimes, so the idea here was to show you that sometimes it's not trivial to find a Nash equilibrium. In this case, we cannot use the procedure of eliminating dominated strategies because here we will not be able to find a dominated strategy. Sometimes there is more than one Nash equilibrium, and I will show you, for example, this is an example that is called, or a game that is called the Battle of the Sexes. And the idea is that a couple plans their vacation. The woman prefers to go to the beach, and the man prefers to go to the mountains, but both prefer to spend the vacations together, not apart. So the payoff matrix for that will be this one. This is for the man, and this is for the woman. So if both go to the mountain, the payoff for the man is 2, and the payoff for the woman is 1. If both go to the beach, the payoff for the man is 1, and the payoff for the woman is 2. But if one goes to the beach and the other to the mountain, the payoff is 0 for both of them. So suppose that I am here. We decided both to go to the mountain. So maybe the woman decides, no, okay, I will go to the beach. But if the woman goes to the beach, they will be here and they will get both. The woman goes to the beach, they will get both payoff 0. So there are no incentive for the woman to go to the beach, and there are no incentive for the man to go to the beach. But suppose that both go to the beach. Again, there are no incentive for the man to go to the mountain or for the woman to go to the mountain. So here we have two Nash equilibrium, going both of them to the mountains or both of them to the beach. So in this game, we have two Nash equilibrium. This is possible. There is nothing that forbids us to have more than one Nash equilibrium. Okay, so a game may have more than one Nash equilibrium. Yes.
In this case, it is kind of the first one who backs off ends up winning less.
Well, yes. Maybe I can. Yeah, I can put -1 and -1. Okay, yes, but it will not change the structure of the game. Yes.
No, but I mean, one prefers mountain, one prefers beach, but if one of them is the more stubborn one,
yes,
ends up winning. It is kind of como dar el brazo a torcer.
Yes. Well, okay. Yeah.
Just to point out.
Yeah, but this is only a model, and okay, but yes, maybe. Which one will be that, the man or woman?
Can you infer from that example, for example, that if you have like symmetric strategy, you will have at least one Nash equilibrium, something like that?
Yes, but this Nash equilibrium is not necessarily written in terms of pure strategies. For example, here, this is a symmetric game. This is a zero-sum game. And apparently, there is no Nash equilibrium. But actually, if we think in terms of mixed strategies, we will find the Nash equilibrium. There is always a Nash equilibrium. But this Nash equilibrium sometimes cannot be written in terms of these pure strategies. But there is always a Nash equilibrium. So you can find always at least one Nash equilibrium. This is for symmetric and asymmetric games. Okay. So what I say that in the case discussed above, the player chooses a specific course of action or strategy and stick with it. This is when we have a given strategy. But sometimes some games, and we have seen one example, in some games, there is no Nash equilibrium in terms of pure strategies. Pure strategies is what I choose as a strategy. I mean, strategy scissor, paper, and stone. But it is essential to incorporate the concept of mixed strategies to be able to find a Nash equilibrium. A mixed strategy is a strategy in which the player randomly chooses between two or more possible options based on a pre-established distribution of probabilities. So, for example, I may have a strategy P that can be written in terms of, for example, alpha strategy scissor plus beta strategy stone plus gamma strategy paper. Okay, so there is a strategy that is not either scissor or stone or paper, but this is a combination of the three. There is a condition for that the sum alpha, beta, and gamma should be greater or equal than 0 because they are probabilities. And okay. And this one, okay? This is something that I need to fulfill. That the addition of the three parameters should be equal to 1, and the three of them should be greater than or equal to 0. Okay. So, for example, I will give an example of matching pennies. Matching pennies is a game where, for example, if I toss a coin, if I get a head, so the player at the column will lose 1, and the player at the file will win 1. If I take tails, why it is not there? Okay. So I take a coin, and what I do is just to toss it twice. If I have or I will toss it only one, but we have to decide. Each player should decide whether it will be a head or a tail. So if the file chooses head and the column chooses head, the payoff will be 1 for the file and -1 for the column. If this one chooses tail and this one chooses head, the payoff will be -1 for the file and 1 for the column. And the same for the rest of the payoff here. So suppose that I start from this situation where both of the players choose tails. So in this situation, both choose tails, so the player at the file will get 1, and the player at the column will get a -1. So the player at the file decides to change the strategy and goes to play heads. When the change is done, now the player at the column is winning 1, and the player at the file is losing 1. So once the situation is reached, the player at the file will decide to change the strategy and go to heads. And now it is the file that is winning 1 and the column that is losing 1. So now the player at the column will go to tails. And then the player at the file will go to tail 2. So we have this cycle, and again, there is no possibility to find a Nash equilibrium here. So what we will do is the following. Suppose that we have a probability P and a probability Q of choosing, in this case, head for the column and Q of choosing head for the file. So file will choose Q head with a probability Q, and tail with a probability 1 minus Q, and the same with the column. The payoff is the same. The payoff head against head is 1 minus 1. The payoff of T against of tail against head is -1, 1. So the payoff is the same one. So I'm not changing the payoff matrix. What I'm saying is that maybe instead of choosing only one strategy, there is a possibility of choosing a mixed strategy, a combination of both. Okay? So in this case, if there is a Nash equilibrium, the players should be able to choose an optimal frequency, an optimal probability here based on what the other individual does. So suppose that we have this situation. Each player plays each strategy with a certain probability, but wants his or her profit to be independent of what the other players does. So if this individual plays heads, this is A and this is B. If A plays heads, B wins. So suppose that I will make the calculation here. So suppose that this individual here, this is A and this is B, and this individual plays, for example, heads. So if I am playing heads, not Q heads, but heads, so the individual here will win the payoff of H versus H with probability P plus 1 minus P, the probability of, sorry, this is T, H. T against T with probability P, and T against H with probability 1 minus P, okay? So forget about this. If this player just decides to play T against the other player will choose this combined strategy. So the payoff of B will be the payoff of T against T with probability P, and the payoff of H against T with probability 1 minus P. So this is what I am saying here. So if A plays heads, B wins minus P, because it's minus 1 here, plus 1 minus P, here it will is a 1. So the payoff of B if A plays heads is minus P plus 1 minus P. If and this is if A plays tails, B wins. So this is when I plays heads, and if A plays tails, the payoff for B will be P, because there is a 1 here, and minus 1 minus P, because there is a minus 1 here. So the idea is that I want the payoff of the player B and the player A to be independent of what the other player does. Because why independent? Because I want to reach a situation where, independently of what the other player does, there is nothing I will win. So this is the Nash equilibrium, because there is no incentive for me to change the strategy. So what I want to do is that this to be independent of what the other player does, and this to be independent of what the other player does. So what I am writing here is, this is the payoff for the player B when A is playing heads, and this is the payoff for B when A is playing tails. And I want these two payoffs to be the same, because I want the payoff of B to be independent of the choice made by A, okay? So I want these two things to be the same, and the answer for this being equal to this is that P should be equal to 1/2. And the same for Q, because this is symmetric. So if I want the payoff of the player A to be independent of the choice of the player B, I need this payoff to be equal to this payoff, and finally Q should be equal to 1/2. So the strategy 1/2 heads, 1/2 tails is the Nash equilibrium of this game. Because if both players are playing this strategy, there is no incentive for any of them to change the strategy, because it will be the same. Because this is what I am doing. I am just trying to look for a situation when there is no incentive for any of them to change the strategy. When I can reach a situation when there is no incentive for each of them, when the payoff that I can get is independent of what the other player is doing, when the opponent is doing. Okay, so this is what I get. For P equal 1/2 and for Q equal 1/2, I reach the Nash equilibrium. Yes.
Bothering again.
Yes.
The way you were playing the game is that the players change the strategy every time,
Yes, yes,
trying to optimize.
yes.
So we have what you have is a transition matrix that is a Markov system in which you know the transitions.
Yes.
And this is a matrix with positive entries. And this matrix has only only one eigenvector which has all the entries which are positive.
Yes.
So I would guess that it is related. That's it's a vector of 4 positions because are the 4 possible outcomes. But it is possibly related to the.
Yes, it is related. I mean, the hypothesis that behind this calculation is that you have the players playing an infinite times, so you want to reach an equilibrium, and this equilibrium, and the way they behave or they play is a sort of Markovian process. And so it is related somehow to that. Yes. So let's go to some formalization of game theory, just to introduce something more formal. Suppose that we have this situation. Each player has at his or her availability the same or not finite set of pure strategies. And so I will call R the set of strategies. So R1 to Rn are all the available strategies to the players. For these strategies, there is a payoff matrix that contains information about the payoff. So there is a payoff matrix that I will call A, and in the elements of the matrix, what I have is the payoff that Ri, the I is here, is the strategy at the file, gets when confronting the strategy Rj, that is the strategy at the column. So I have a set of strategies that goes from R1 to Rn, and I have a matrix that is n times n, and the elements of the matrix are containing information about the payoff of a given strategy against another strategy. We can also define, in the way we did here, we can define mixed strategies. A player can adopt any of the pure strategies, but can also adopt a mixed strategy. A mixed strategy is a strategy that is not written in terms of this, is not any of these strategies, but this is a combination of the pure strategies that I have. So when I formulate the game and I say, what are the strategies available to the players, I am talking about pure strategies. But also, there is a possibility of adopting a mixed strategy. A mixed strategy is a combination of all these strategies. But this combination cannot be anything I want. This combination should be something that is written like here in terms of the probability of adopting strategy 1 or the fraction with which adopt strategy 1, then strategy 2, and then strategy n. And these numbers, as I mentioned here, are probabilities. So this number should be greater or equal than 0 and greater and equal than, less and equal than 1. So these should be positive numbers. They cannot be greater than 1, but I can just ignore this condition by writing this. If I include this condition, there is no necessity of including this condition here. The addition of, or the sum of all the value pi should be equal to 1, because this is a probability. So the addition of the probability should be equal to 1. So a given mixed strategy has this form. It can be written in terms of the other strategies with numbers P1 to Pn. P1 represents the probability of adopting the strategy R1. P2 represents the probability of adopting the strategy R2, and so on. But the condition is that the addition or the sum of all this Py should be equal to 1, and this Py should be greater or equal than 0. Suppose that we have, for example, a situation with 3 strategies. Yes?
In here, we're assuming that each player has the same
Yes.
set of strategies.
Yes, in this case, for this situation, I can assume that the players may have different strategies, but for simplicity, I will consider the situation where both players have the same set of strategies, just for simplicity. So suppose that I have a situation when I have 3 strategies, R1, R2, and R3. So it is a game like the scissors, paper, and stone, where I have only 3 strategies. And what I am going to do is the following. I will represent in a 3-dimensional space this vector, the vector P that is equal to, in this case, P1, P2, and P3. Okay? Any pure strategies can be represented as a point in this 3-dimensional space.
Can I ask something? Like,
yes.
Each player can have like different probability vectors as well.
Yes, yes,
Okay.
yes.
Just
This is, yeah. The only thing that the players have is the same set of possibilities, but they can choose different mixed strategies.
Yeah. Okay, thanks.
So suppose that this is 1, this is 1, and this is 1. So as P should be always positive, so there will be not point here or here or here. There will be only points here where these values can be positive. But also I have another constraint, that is that the addition or the sum of Py should be equal to 1. This gives me something like that. This gives me a set of points that will be on the face of this tetrahedron, not inside, but only this face. Okay? This face here is the situation when P1, P2, and P3 are greater or equal than 0, and also the addition of Py is equal to 1. These 2 conditions give me this set that in this 3-dimensional space has dimension 2. It's only this face, okay? Not the volume, but only this face here. This is called a simplex. And for example, this point here corresponds to a pure strategy because it is 1 or 0, 1, 1, or no, 0, 1, 0. This corresponds to another pure strategy, and this corresponds to another pure strategy. This, for example, could be the 1, 0, 0. That means that I have R1. This corresponds to 0, 1, 0. I have R2. And this corresponds to 0, 0, 1. That is R3. So these points are the pure strategies. And the other points in this side, in this face, are the rest of the mixed strategies. Okay? This is a representation of the strategies as vectors in a 3-dimensional space because I am dealing with 3 strategies. And this is called simplex. When I analyze the dynamics of a game, this is something that will come later, if I analyze how the strategies are changing, the orbits of these changes should be always here, on this surface. I cannot go out, because if I go out, that means that one of these numbers P is greater than 1. So I am trapped within this surface. All the strategies should be here. And if I change strategy, the strategy should be here. There is no possibility. It is forbidden for me to be outside this triangle. Okay? Because if I am outside, I am violating these 2 conditions. So if I want to calculate the payoff of any strategy P1 against another strategy P2, the only thing I need to do is just to make this multiplication of the vector P1 that is the vector that is representing the mixed or pure strategy 1. Here I have the payoff matrix, and here I have the vector P2, representing the mixed strategy 2. So if I want to calculate the payoff of any strategy P1 against another strategy P2, the only thing I need to do is just this calculation. So it's P1 multiplied by the matrix, the payoff matrix, multiplied by the vector P2. This will give me then the payoff of P1 against the strategy P2. If I have a pure strategy Ri, that means that instead of having a vector with all the components different from 0, or more than one component different from 0, I have only one component that is equal to 1 and the rest is equal to 0, so I will be in the case where P1 is a pure strategy. In this case, this vector will have this form, will be a canonical vector with only one component different from 0 and being equal to 1. And to get the payoff of this pure strategy, what I need to do is to multiply this vector again by the matrix and also by the, this is a 2 here. This is a wrong, this M is, okay, this is confronting P1. This is P1. And this is the same as here. The only difference is that instead of this sum being for any value of I, this sum will be only for one value of I, that will be the corresponding value to the pure strategy here. So instead of having a double index, I have only one index here, and the payoff of a pure strategy against another strategy is calculated this way. And by definition, I will call this payoff, that is the payoff of a pure strategy against any strategy, in this way. So this is only a definition. Okay, but this gives me a way of calculating the payoff of any mixed strategy against another mixed strategy using the payoff matrix. And now we can see the utility of the payoff matrix, because it allows me to calculate very quickly the payoff of any strategy against any other strategy. Okay. So we can come back to the concept of the best response. And again, a best response to a strategy P1 is a strategy P2 such that the payoff of P2 against P1 is a maximum. That was the definition of the best response. The definition was that if I am confronting P1, the best response to P1 is a strategy P2 that has the maximum possible payoff when confronting P1. So that means that the payoff of P2 against P1 is a maximum, okay? Suppose, again, that we have a situation when all the players have the same strategic choices. That means that the set of strategies for all the players is the same, okay? In this case, a Nash equilibrium is a strategy that is the best response to itself. That was the definition of the Nash equilibrium. So in terms of this formalism, a Nash equilibrium is a strategy, for example, strategy Y in this case, such that the payoff of any other strategy against I is lower than the payoff of I against itself. So if this payoff for any strategy J here is lower than the payoff of Py against itself, so we are saying that this strategy I is a Nash equilibrium, okay? So this is the definition of Nash equilibrium, and this is a formalism, or the formal way to define the Nash equilibrium. So, and you can see that here it is not greater than, but it's greater or equal. So if what I have here is greater or equal, I will talk about a Nash equilibrium. But if I can say that this is a strict greater than, and there is no equal here, that means that the highest payoff of any strategy against this strategy is itself. For example, in this case, if the highest payoff of the strategy Pi will be obtained by Pi itself and no other strategy, and so this is greater than, we are talking about a strict Nash equilibrium. So if this is the condition that is fulfilled, and here I have greater or equal, So I am talking about a Nash equilibrium. So I will say that PI is a Nash equilibrium. If I have here greater than, strict greater than, so we will say that PI is a strict Nash equilibrium. So this is the difference between a Nash equilibrium or a strict Nash equilibrium. Okay. The central question of evolutionary game theory is whether there is a profile of strategies in a population that is stable against perturbation. That is, if it is invaded by mutants, can they take advantage? So why I am trying to define a Nash equilibrium or a strict Nash equilibrium and trying to work with strategies and game theory. One of the key questions for example, in game theory is the following. Suppose that...
I have a question.
Yes.
In here we're saying basically that a Nash equilibrium is when all players do the same strategy and they don't want to change the strategy. Because we're saying the PI,
yes.
API is the maximum.
Yes.
But can it happen that one player, if one player supposes that player, if player 1 supposes that player 2 will choose strategy 1, and player 2 supposes that player 1 does strategy 2, something like that?
Yes.
Can it happen that the maximum is in a mixed state, like in a chicken game, for example?
Well, yes. Here, P is a mixed strategy. It's not necessarily a pure strategy.
No. I mean that in here we say that a Nash equilibrium is necessary that all players follow the same strategy.
Yes.
But
No. I am assuming, no, what I am saying here is that I assume that all the players have the same set of possibilities, okay?
Then I think then that the second PI, it should be like P2 or P1 or something like that. Because there it says that the maximum is that both players always do PI. I don't know if I'm explaining myself.
No. What I'm saying is the following. Suppose that I have player 1. And this player is choosing strategic P1, okay? And I have player 2. And this player is choosing strategy P2, okay? If P1 is a Nash equilibrium, then P2 versus P1 should get a payoff that is lower than or equal to P1 to P1. This is what I'm saying. Okay. It is independent of what is the choice of this. This is something that is inherent to the game, not inherent to the choice of the players. Okay?
But I mean,
if this is the situation, so player 2 will change the strategy and will go to this one.
But the Nash equilibrium, I believe it isn't just P1. It will be in the supposition that the other player will do such strategy. So the Nash equilibrium would not be P1, it would be P1.
You're getting confusing with this strategy and the possibility.
Yes.
So
yes.
They might have the same strategy, but they might have different possibilities. So when you add them up, you're going to end up with the one probability, you know? So when you get in the Nash equilibrium, so it follows that rule, you know? So, yeah.
So this is the definition. It is independent of what the players is doing. This is something that is inherent to the game, okay? So what I'm saying here is that given that there is, you take strategy, don't talk about players. Given that there is strategy P1, so which is the other strategy that in response to P1 will get the highest payoff. Okay. If this strategy turns to be P1, so P1 is a Nash equilibrium. It could be that there is another strategy, together with P1 that will get the highest payoff. For example, there will be strategy P3 that against P1 gets the same payoff than P1 against P1. So in that case, instead of having a strict higher here, you will get higher or equal. Okay? So in this situation, when you have here higher or equal, you have a Nash equilibrium. If you have higher than, a strict higher than, you will get a strict Nash equilibrium. Okay, this is the definition. Okay. There are no players involved here. Okay.
Just a question. I think
Yes.
it's related to his question.
Yes.
Like all players have the same set of strategies.
Yeah. In
but
this case, yeah, all players have the same choice of strategies.
No, yeah, but
Yes.
I assume that if the payoff matrix is symmetric, then like the Nash equilibrium would be the same for all players. And
Yes. Yes.
and if like the
Yes.
payoff matrix can introduce asymmetries.
Yes.
It's kind of,
Yes.
that's-
Yeah. If the players have the same strategies, the payoff matrix should be symmetric, because there is no difference in that. Okay, this is what we are saying. When you are saying that all the players have the same choice of strategies, you are somehow saying that the payoff matrix is symmetric. It's almost the same thing. Okay, yeah.
When we're thinking about the Nash equilibrium from the perspective of a game,
Yes.
so you play something and the other play something, and
Yes.
you both play a lot, and then you find a equilibrium,
Yes.
right? So we're assuming rationality.
Yes.
When we're dealing with some games, like you said, like you can treat like bounded rationality. So in these games, we don't have Nash equilibrium.
No. Or
Okay.
you may have one, but you cannot make the calculations we are going to do now.
Okay.
Here you are assuming that you have a rational player, and the only thing that rules the behavior of the player is the payoff matrix.
Okay.
And the player will always choose to get the highest payoff. So this is the assumption that is rationality. Okay. So suppose the following. Let's move to. Okay. Suppose the following. Suppose that. Well, this is quite hard. So I will move from here. This is not important. Suppose that the population adopts a unique strategy. So all the population is adopting one strategy. Okay, so I have a population, and all individuals in the population decide to choose strategy P. Okay? And suddenly there is a mutant that comes with a different strategy. And the strategy that this mutant is adopting is P not, for example. So what I'm saying is the following. If by mutation or invasion, an individual in the population adopts a different strategy, so this is the new strategy. If the mutant is doing better than the rest of the population, so if this strategy is better than the strategy that was adopted by the population, all the population will move and will decide to adopt the new strategy, or will move or will be invaded by this new mutant, because it will have a highest fitness, so this mutant will invade all the population. So, if the mutant is doing better than the rest of the population will imitate and it change the original strategy. If, on the contrary, if this individual with this new strategy it goes worse than the strategy that was already adopted by the population, so the rest of the population will ignore it. So if I come with a new strategy and this strategy is not good enough, so there is no incentive for me to change the strategy. I will go on with the strategy that I have already adopted. So we said that if the population adopted the strategy such that no mutant strategy can take advantage of the situation, that strategy is called an evolutionary stable strategy. What I'm saying is that for any other P naught or P hat strategy, for any strategy, for any mutant, this strategy will be always better. Okay? If this is the situation, so I will say that the population has adopted an evolutionary stable strategy, because there is no possibility that a mutant will invade the population and make the population to change the strategy to the new one. Okay? So what I am saying is that an evolutionary stable strategy is a population that has adopted a given strategy and no mutant can take advantage from this strategy. So let's go and make some calculations to see which are the conditions for a strategy to be evolutionarily stable. Okay. So suppose that the population has the strategy I'm changing letters, but suppose that this is Ri, and there is an invasion of another population, a mutant, with a strategy Rj. So this is the mutant, and this is the old strategy. So what I want is that the payoff of this strategy against the population is less than the payoff of this strategy against the population. So at the beginning, all the population was adopting strategy Ri, but now I have a mutant. So I will say that at the beginning, all the population was like this. All the population was adopting the strategy Ri, but now I have a population that is like that. Okay, because there is a mutant, epsilon is very small, so there is only one mutant or a small quantity of mutants that are entering the population with this strategy. So the composition of the population at the beginning was like this, was all the population adopting the same strategy, and now I have something like that. There is a fraction of the population that is equal to 1 minus epsilon that is adopting the strategy Ri, and there is a fraction of population epsilon that is adopting the strategy Rj. So what I'm going to analyze is what is the payoff of Rj in the population and the payoff of Ri in the population. And what I need, if I am asking to Ri to be evolutionarily stable, what I need to happen is the following. I need, as it is written there, that the payoff of Ri against the population, that is R. This is the payoff of Ri. This is the payoff matrix. This is the payoff of Ri, and this is the payoff of the whole population. So I want this payoff to be greater than this payoff. Okay, this is what I want, and this is what I have written here. I want the payoff. Okay, this is the other way, but I want this payoff to be greater than this payoff. Okay, this is the condition for Ri to be evolutionarily stable, meaning that for any strategy Rj, the payoff of J being different from I, the payoff of Ri against the population is greater than the payoff of Rj against the population. So let's move this expression and write this. I will move this from here to here, and now I have the following. I have 1 minus epsilon times Ri against Ri minus Rj against Ri. So I am just accommodating the expression here, plus epsilon times Ri against Rj minus Rj against Rj. So this is the same as this, just reaccommodating the terms. So I need this whole expression to be greater than 0. Now, suppose that epsilon is really very small. So if this is greater than 0, I can say that a condition for this to be greater than 0 is that as epsilon is very small, I need this to be greater than 0. Okay? If this is greater than 0, so as epsilon is very small, the whole expression will be greater than 0. So if this is, unless this is equal to 0, if this is equal to 0, I can say nothing. But if this is different from 0, and I want this, the whole expression, to be greater than 0, it is enough with asking that this be greater than 0. And this being greater than 0 means that this term here, the payoff of Ri against Ri, should be greater than the payoff of Rj against Ri. It sounds familiar. This is the definition of strict Nash equilibrium. So if I want this strategy to be an evolutionary stable strategy, I need this strategy to be a strict Nash equilibrium. But suppose that it is not a strict Nash equilibrium. Suppose that this is not equal to 0. This is equal to 0. That means that it is a Nash equilibrium, but it's not a strict Nash equilibrium. So if this is equal to 0, I need to ask this term to be greater than 0. Okay? So if this is equal to 0, meaning that the strategy Ri is not a strict Nash equilibrium, so I need this to be greater than 0. And asking this to be greater than 0 is the same as asking that the payoff of Ri against Rj is greater than the payoff of Rj against Rj. That means that Rj is not a Nash equilibrium because the payoff of Rj against Rj is not the greatest one because this payoff is greater than this payoff. So what I'm saying is that if it is not a strict Nash equilibrium, what I need is to be the other invading strategy not to be a Nash equilibrium. And this is called the stability condition. So a strategy to be an evolutionary stable strategy should be or a strict Nash equilibrium or be a stable Nash equilibrium. So if this condition is fulfilled, what I'm saying is that this strategy is a strict Nash equilibrium. But if this condition is not fulfilled because this is equal to 0, so I need to fulfill this situation or this condition, and this condition is called the stability condition, and then Ri is a stable Nash equilibrium. So by doing that, we can link the idea of evolutionary stable strategy to the concept of a Nash equilibrium. So, yes.
That you want to make a stable diversity, in this case, of strategies, for example.
Yes.
The only way in this case will be just changing or adding a sessionality, for example, in the payoff matrix.
For example, yes.
Perfect. Yeah,
yes.
Just
yeah, but there's another thing that is important, and is that to be able to show this and to make this calculation, I was always saying that epsilon was small. So what I'm saying is that there is a sort of threshold of stability. So a strategy can be an evolutionary stable strategy if it is invaded only by a small quantity of a mutant. But if this amount is very big, so maybe this situation will not work because epsilon is no longer small. So I cannot do what I did in the first step. So there is a sort of threshold, or there is a sort of basin in which this thing is valid. If the invasion is very big, so there is a possibility that even a Nash equilibrium could be invaded. If this happens, it's because the invading strategy is itself a Nash equilibrium, for example. So there is a possibility of invasion even if the strategy is a Nash equilibrium. But for that, you need a big invasion, not a very small one. So that's why it is important to understand that epsilon in this demonstration or in this development, epsilon is very small. If epsilon is not small, this is not valid. Okay. So let's go to examples. So we have, just to make a summary, we have the definition of best response, we have the definition of Nash equilibrium, we have the definition of strict Nash equilibrium, and the definition of an evolutionary stable strategy. These concepts are very important, and we have already seen how they appear within the frame of game theory. Let's go to some examples. This is a very known game. It is called the Hawks and Doves. And the formulation of the game is the following. There are two individuals that must compete for a valuable resource. And there are two different strategies. The strategies are called Hawk and Dove. The Hawk always fights for the resources. If the Hawk wins, then the Hawk receives a benefit. But if the Hawk loses, it may suffer an injury because of the confrontation and must pay the cost of this assault. So this will be reflected in the payoff matrix. I will write the payoff matrix, and this will be clear. On the contrary, the dove never fights for the resources. The dove retreats if it is confronted by a hawk, and if it is confronted by another dove, what they do is to split the resources. Okay, and there is no cost of aggression because there is never a fight. So the payoff matrix is something like that. If a hawk is confronting a hawk, we can say that statistically half of the times it will win and half of the time it will lose. When it wins, it gets a payoff equal to chi, that is the gain for obtaining the resource. And when it loses, it gets a cost, or it should pay a cost that is equal to c, that is the cost per aggression. Okay? So the total payoff will be equal to chi minus c divided by 2. I don't know what is this thing here. This is wrong. Okay. This should be the same. It should be chi minus c over 2. There is a problem here. These two terms should be equal. Okay. So a hawk confronting a hawk will get a payoff that is the mean value between the gain for obtaining the resource and the cost for losing and having to pay the cost of the assault. Okay. On the other way, if a hawk is confronting a dove, it always wins because the dove is not confronting. The hawk just retires from the confrontation and does nothing. So the hawk will get the whole. I will use the blackboard because there are some inconsistencies in the matrix. So this is hawk, dove, and dove. So here we have chi minus c over 2. Here we have chi and 0. This should be a chi, not a b, like that. Here we have 0, and here we have chi divided by 2. So if a hawk is confronting a hawk, it should pay the cost if it loses the confrontation, and will gain chi if it gains the confrontation. As the probability of winning or losing is 1/2, so the payoff is the mean value of this situation. If a hawk is confronting a dove, it will get chi, because the dove is doing nothing, so the hawk will gain the whole reward. If a dove is confronting a hawk, the dove will get nothing, so the payoff is equal to 0. And if a dove is confronting a dove, they split the gain, so the gains will be chi over 2 for each of them. So this is the payoff matrix. There is a mistake there with the letters. So let's go on working with this matrix here. Suppose that chi is greater than c. Okay? Suppose that this is the situation. So if this is the situation, this is positive. So this would be greater than 0. and C would be greater than C over 2. So if C is greater than C, this strategy is dominated by this one, so there is a very clear result. Both of them will choose to play hawk, okay? So if G is greater than C, there is a dominating strategy that is hawk. But this is not what we want. We want we want a game to be more interesting like that. So what we are going to do is to say that G is less than C. So the cost is greater than the gain. In this case, so this is negative, so 0 is greater than this value, but this is greater than this one, so there is no way to find a dominating strategy. So in this way, it is clear that hawk is the dominating strategy and hawk is the Nash equilibrium of this game. But we are going to work with this situation, where G is less than C, so we cannot find a dominating strategy, so we cannot find a Nash equilibrium in terms of these pure strategies. We will show later that there is a Nash equilibrium, but this Nash equilibrium is written in terms of a combination of hawk and dove. It will be a mixed strategy. So the Nash equilibrium for this game will be a mixed strategy and not a pure strategy, okay? So, okay, what is written there is what I have explained here. If G is greater than C, so the only Nash, we have one Nash equilibrium, and this is hawk, but we are trying to work with a situation where G is less than C, so there is no a dominated or dominant strategy, okay? So this is more or less what I explained there. So if C is greater than C, neither H, neither hawk, neither dove is an evolutionary stable strategy. Why not? Because for being an evolutionary stable strategy, I need hawk to be a Nash equilibrium or dove to be a Nash equilibrium. And they are not Nash equilibrium because they are not dominating strategies. So what is here, which is here, I want to find this Nash equilibrium. And for that, what I am going to do is something similar to what I did before. I want to find a mixed strategy. I will call this mixed strategy P, that will be equal to an amount 1 minus P of playing dove and an amount P of playing hawk. So I will try to find a strategy that is a mixed strategy and see whether for a given value of P, I can show that this strategy is a Nash equilibrium, okay? But we are at 6, and I will not be responsible for you being late for dinner, so we will stop here and go on tomorrow, okay?